This is part 2 in my project where I want to be able to have a device that sits on a picnic table when I'm out camping with my Scamp, and select like a star or a planet and have it automatically point a little laser at that point in the sky so I can do some astronomy with some binoculars. Now in part 1 I got as far as getting a lot of the hardware together. You can see it running here with menus and a gimbal that has a laser attached to it, so I think I'm okay for the basic drivers. I've now mounted on a better piece of wood, looks a bit nicer. I put some varnish on it. I put some leveling screws, legs underneath it so I can level it a bit, and you can actually see the gimbal working with some of the new logic where it can now be positioned to any point in the sky, and we'll have a look at how that's done later. Now I need to get started on the actual coding. So this diagram sort of shows how I'm thinking the whole thing's going to work. So at setup it's going to get things like the location and work out where north is based on a GPS. And then I'll show top level menu where it allows you to select an object you want to look at from a list of planets, constellations, satellites and stars. And then I showed under planets, sort of thing it has to do is go out to some software and get the location of those planets and show the list of planets that are available on a menu. Once one of those planets is selected, in this case, it moves the laser to that point in the sky. Then after that it does a little cleanup, goes back to the top level menu and does the same thing for constellations, satellites and stars, but some of the logic for getting the list of those is going to be a little different. So for the next piece of code I'm going to dig into a class that's going to set the laser position, so the azimuth and the altitude of where it's pointing in the sky. Now this class also has to include some calibration logic to make sure the servos are actually pointing at the right azimuth and altitude. A quick bit of theory here. So in astronomy I'm going to use altitude azimuth coordinates for pointing the servo. So the idea is based on facing true north, the azimuth is the number of degrees from clockwise from true north, and the altitude is the number of degrees from the horizon. And using azimuth and altitude is it's good because the SkyField API, which I will be using for getting planet positions, provides that as part of the code. And here's a little bit of demo code they show you where it's getting the altitude and the azimuth for a particular object in the sky. First little class I needed to put together was a class where it takes astronomical azimuth and altitude and converts it into angles that the servo uses. And on the gimbal, the servos really just rotate from 0 to 180 for the azimuth or the horizontal direction. I don't have it, and it's not able to turn a whole 360 degrees. To be able to get the astronomical 360 degrees, I need to reposition this to start from true north, which would be astronomical 0 for the azimuth, and be able to simulate going through 360 degrees. So I do that by moving the actual gimbal between 0 and 180 degrees, and then changing the altitude or the second servo on the gimbal to swing between 0 and 180 degrees. So if it's doing this bottom quadrants of the astronomical azimuth, so from 180 up to 270 degrees, then it's going to swing the altitude servo, basically start from 180 degrees and work back to 90 degrees, the opposite direction. So there's some translations that's going to be needed in the code depending on what quadrant I'm asking it to move to in the astronomical azimuth and altitude. I need to convert it to angles that the servo understands. And this is a little table I put together of what those some test conversions would look like, so I can use that for testing it. Bit of explanation of what I'm doing. So this shows the class I created to be able to move the gimbal, so feeding it astronomical, azimuth and altitude, and getting it to convert it to servo angles to point at the right part of the sky. So class really just had two functions in it: the init function, where it first sets up the servo hardware to make sure that the servos were actually swinging for 180 degrees and starting at the right position and ending at the right position. I put settings for the minimum and maximum values for the servo into a settings.json file, so I retrieved that and set the servo minimums and maximums for the duty cycle. And then the actual code for moving it is, I have a move method, takes a astronomical, azimuth and altitude. Depending on what quadrant the azimuth is in, it does one of these translations. And just a note on here, so from 90 to actually 270, so the bottom azimuth quadrants, the translations are exactly the same, so I simplified that in the code. Let's have a quick look at the code. So starting from the bottom, I added a settings manager class. I actually got an AI to write this, but it seems to work okay. Basically it's looking into a settings.json file, and we'll return whatever value for one of these settings that I request. So the settings I'm using here is the azimuth minimum and maximum pulse width, and the altitude minimum and maximum pulse width to give 0 to 180 degrees of movement, starting from the locations that I want them to start from. So these seem to be the values that work for me at the moment. And this is used in the Gimble manager. So this is that class I just showed, where first in the init it sets up the servo, sets the minimum maximum range from those settings we got from the settings manager, and then the move logic is here. So like I showed in there, so there's actually 4 quadrants. 2 of the quadrants have the same translation, so from 90 degrees to 170 degrees azimuth, it can just use the same translations, but from 0 to 90 and 270 to 360 degrees azimuth, it needs to translate the values to values that the servos will use on the gimbal. And then I just set it, and I actually put a sleep in here just to make sure it doesn't go off and do something else while it's still moving the gimbal around. Then I also made a little gimbal tester program, so I wanted to make sure things were pointing in the right direction when I moved it through different altitudes and azimuths, or astronomical ones. So this first one here, where I'm testing the altitude, servos moving correctly and pointing it the right direction, I move between 0 and 90 degrees when the azimuth is 0, and then just to test the other side of the quadrants, when it's at 180 degrees, I move from 45 degrees to 0 position. And there's also a test routine in here for testing the azimuth, so really just moving the azimuth servo through 360 degrees. So this is where I'm using the GM tester to actually test that the gimbal movements are what I expect, in this case for the altitude positions. And then I also did a test for the azimuth positions, make sure it moves through the azimuth positions the way it should and generally pointing in the right direction. I'm going to have a little break here. I'm actually going to flip over and just go through some of the highlights of the final code I did. And I also simplified the actual code in the project. I got rid of a lot of the test Python routines I had in there. But I put the links to the 2 versions of GitHub, so when I still had all the extra code in there to test things, and then I'll just show the final code GitHub repository as well, and that'll all be in the description. Just to give you an idea what the end result looks like. So there's all our top level menus. We can select from planets, and it'll move the laser. You can select from satellites. Those are the only 2 visible at the moment, so only 2 are shown. Select from constellations. Again, only shows visible constellations. And you can select from stars, and shows just the top 35 brightest stars that are in the sky at the moment. Other things you can do in setup, you can just move the laser to a particular position. You can also download the data, and you can get a status as well. It shows you the latitude and longitude, GPS settings, the real-time clock settings, and you can exit, which will also reset the laser position. So just a reminder, I cleaned up a lot of the source files in GitHub. So I put the link to this version, which was before I cleaned up all the source files. So it has all the little test programs that I used while I was working out how to get everything working. And then this is the new version, which is just straight under skyLaser in my GitHub. Okay, now we can have a look at some of the classes in my project. So this is VS Code now. Look at that simplified project structure. And the classes I'm going to look at is the Celestial Manager, which does does all the calculations about where stars are, and it's using the SkyField module to do that. So that's all wrapped up in a class, and then we'll have another look at the skyLaser.py class, which is the main one that runs everything and makes use of these other classes. So you see here in Celestial Manager, it's importing a lot of SkyField modules. So let's have a look at what SkyField is. SkyField, so this is an astronomy module. So it does things like calculating where stars and planets and things are, and can do things like from a particular position on the surface of the Earth, work out what azimuth and altitude that star or that celestial object will be at. It also contains good interfaces to a lot of base data, things like planets and stars and satellites, and ways of working with them. So let's look at this Celestial Manager class. So I import a bunch of SkyField components, date and time, and some other things. So the first few classes I defined in this file are things to hold basic record definitions for things like satellites and planets and constellations. And then we get into the main Celestial Manager. So Celestial Manager, it's just setting up some basic information that gets passed to it. So where it currently is, that's coming from the GPS module, the current date and time, and then does some loads of data if it needs to. So things like this ephemeris and this Hippocos. So the ephemeris, this D4211, is information about planets. So remember, planets move independently of where the Earth is. Satellites are the same. They're fairly dynamic and change position all the time, whereas stars are fairly static in the sky. You don't see them moving between different parts and constellations and things like that. So these sources of information has information about these different things. This Hippocos is a pretty interesting one. It's came from exploratory satellite that was mapping all the stars in the sky. So it's really large. It's 160 or so thousand objects in it. I don't use all those, but I use it to cut down and just get the list of the 35 or so brightest objects in the sky. So I'll load all those up, and just to let you know, this takes a while to do. And then based on that information, I also build a list of satellites by calling the build satellites function. Get a list of brightest stars. So this is my 35 or so brightest stars that I want to keep track of. List of constellations and a list of planets. So there's some properties defined here where I can after I've done all the work here, I can go and pull the list of bright stars, the list of constellation, list of satellites, and so on. And then there's various build functions. So for example, this build satellites function, I manually enter some interesting satellites to put in there. A lot of these satellites aren't going to be visible at the particular time and location that I'm looking for them. They, pass overhead, pass too low, aren't bright enough, all sorts of reasons that a satellite may not be there. But a couple of these geostationary satellites, like this ViaSat and AMC3, they'll always show up because they're always in a standard place in the sky. But these other ones, it's luck of the draw on when you do it, whether you can see them or not, and whether they'll be displayed on the list of satellites. So make a satellite and add it to the list. Among the things that I do when I make a satellite record is I check where its apparent position is. So based on where I am, where that satellite would be. So I'm looking for things like, is it above the horizon? And actually, if you look in my settings JSON, you see I've got some cutoffs for the horizon, so I don't go right down to 0 degrees altitude. I go down to about 10 degrees because that usually is about as closest to the horizon that I can see from where I'm standing. There's usually going to be trees or mountains or something in the way, so I don't bother trying to get right down to the looking for objects that might be just sitting on the horizon. Same sort of thing for constellations. I build the list of constellations based on a known star in the constellation, and I'm using that star catalog to find out where it is. Same idea. If the constellation isn't above the minimum level above the horizon, it won't be shown. So when I go into my menus on the device, it won't show all these constellations all the time. Same thing for planets. List of planets, I call them out, and the planets I include the sun and the moon as planets, so can point to those as well. And then the final thing I do is get a list of bright stars, and so I'm using the pandas data management module. It's included as part of SkyField and allows me to sort and select data from the Hipparchus. I use it to get the list of the brightest stars, and I have a magnitude cutoff. So I think it's anything above about magnitude 2 or less than magnitude 2, because it gets brighter the lower the number is. I'm selecting, and I select about 30 or so of those. Again, only show the stars that will be visible, because I'm not interested in ones that are in the southern hemisphere. I won't see those, and I'm not interested in ones that are so not bright enough to be seen with the naked eye. So usually get about 30 or so stars show up on that one. So that's about it for the Celestial Navigator, and then you'll see in this main routine here, if I just run Celestial Manager, do Python selestralManager.py, it'll run this routine in here, which tests out all the different functions in here and prints out the list of stars, constellations, planets, and satellites that it's found. About the only other functions in here that I use a lot are things like get planet apparent coordinate, because after I've filled up the menu, it may be half an hour later during a session with the astronomy, that I actually go select a certain planet or star or something to look at, and its position may have changed, so I recalculate where its apparent position is at that time as well, to make sure it points as accurately as possible at that planet. So the other piece of code that I want to look at, so this is the main one, and I run it with a cron job when the application starts up. So let's just run through, see what it's doing. So it imports all the important classes I've put together. First thing it does is check whether it's got internet access, and sets up the download manager. You'll see there's these files here: satellite CVS, hip which is the Hipparchus data, and DE 421, which is a JPL file with information about planets and things in it. They need to be refreshed every so often. Probably this Hippocos not so often, but things like satellites, the information that changes fairly rapidly. Satellites can change their orbits due to all sorts of reasons. They could be repositioned, and they could also be impacted by things like the atmosphere. So usually what I do if I'm going out doing one of these astronomy sessions is I'll download these things, at least the satellites and the DE 421 file before I start, so it's with me. But it will go out, and first thing it does is when it starts up, it'll check whether any of those files are missing. If any of them are missing and it has internet access, it'll try and download those files. If a file's missing, I don't have internet access, it's not possible to download it, so I can't really run my program, so it just gives me an error message and exits. Next thing, it starts up. First thing I need to do is get GPS information, like where I am and what time it is. And so I'm using the GPS class to do that. That's this GPS Manager class here. And I'm doing read GPS until I get a good information back to say that it's found my location, altitude, and time. I actually go through that 3 times. Sometimes when I'm in a new location, it takes a while for the GPS to find GPS satellites and settle down and work. So it can take up to 3 minutes to go through this process. If it's already just done it, usually I'll just find GPS satellites immediately. Seems to be pretty good about that. The other thing that's happening in the GPS Manager, I won't show you, but there's a real-time clock. So I get the time off the GPS satellite initially when the program starts up, and then I also keep track of what's the difference between that and the internal real-time clock of the Raspberry Pi. And I'm going to use that corrected real-time clock time, so reference to the GPS, to all my calculations after that, so it should have a pretty accurate time for anything I do after I've got the time off the GPS. Does all the loading of celestial data, and then we get into the main loop, and let's jump down here to the main loop. So the main code, while true, it's just going to loop through here, and this we saw in the design. So depending on the menu selected from the top level menu, it'll do setup, it'll show stars, show satellites, show constellations, show planets, or else it'll exit and it'll also reposition the laser at that point, just to make it easier to put away and store. So let's have a look at example of this. Let's have a look at do stars, probably a good one. So do stars. So in this case, if I've decided I want to see stars, then it builds up a new list of menu items of these bright stars, and we saw it up in the Celestial Manager where it builds up its list of bright stars, displays those menu items. When one of the items is selected, it'll reevaluate the apparent coordinate for that item. So again, if its position's changed a bit, or the Earth's moved a bit since when I first started up this skyLaser, then it'll recalculate the apparent coordinate based on the current time, and then it'll move the laser to point at that object, display a bit of information about what I'm pointing at for 5 seconds, and then drop back down into this main menu. And basically it's doing that for stars, satellites, constellations, and planets. And then let's just have a look at this bit of code to set up. So this just has some options for setting up the skyLaser. So one is to point the laser at various positions in the sky, and this I just used when I'm trying to work out whether it's pointing at the right direction, whether 180 degrees on my as a coordinate is actually getting the skyLaser to point to that, or else I can adjust the settings to, if something needs correcting. Then some other options here are if we have internet, it shows the options to be able to download data. And here's where it, based on what option was selected from the setup menu, it does one of those things to depend on the item ID that was selected. So just some photos of my last trip. I went up to Promised Land State Park in Pennsylvania. It was early in the season. It's fairly high, so I set the skyLaser up on a rock that had fairly clear line of sight around it. I used my iPhone's compass to find out where true north was, and here's some photos of skyLaser firing away. Pretty hard to take these photos at night, so there's no movies. And then this final one, I'm actually looking at Procyon star, which is one of the brightest ones in the sky. You can see the skyLaser's out by a tiny bit, but mostly points to the star, so I'd be able to find it in the night sky if I was using the skyLaser.